Let us look at logical connectives and truth tables, right? So, what is logical connectives? That is the I mean uh, the propositions are obtained by starting with given propositions, right? So, like not, if, then, and if and only if. Right? Such words or phrases are called logical connectives. Okay, so let us look at first the propositions, or the which is called negation. Right. So a proposition which is inserting a word not at the appropriate place for the given proposition is called the negation. So the negation of suppose P is a proposition and this is not P, right? Which is read as not P. Okay. For example, if I take one example as 3 is a prime number, right? 3 is a prime number. So if I call this as P proposition, right? So not P would be 3 is not a prime number. Right? Okay, and let us look at the truth table for this. Okay, so for the proposition which is if P is true, then not P is false. So if P is false, then not P is true. In other words, if the truth value of P is 1, okay, then the truth value of not P is 0. Okay, so P and not P, right? So this is 0, this is 1, not P, and 1, this is 0. Okay. Now let us look at conjunction, right? A compound proposition obtained by combining two given proportion by inserting the word which is and in between that. So this is called as conjunction of the given proposition. And suppose if I consider a P and Q, right, and Q, so which is also denoted by P and Q, right? So the symbol this refers to and. Okay, and let us write the truth table for this. So the truth table for this P and Q, since we have P and Q as propositions, so P and Q. Okay, yeah. So 0 0 gives 0, and this is 0 1, so this is also 0, and this 1 0, and this is 0. So both are true, then the final result will be true. Okay, so let us look at a few examples for this positions. Okay, suppose if I consider P as root 2, E is an irrational number. Okay, irrational number. I'll consider Q, right? 9 is a prime number. Okay, so if you put this P and Q, okay, that would be root 2 is an irrational number, uh, which is true. Okay, and 9 is a prime number, which is false. So this being true and this being false. Okay, here. So uh, when false gives false, right? So we have seen this. Okay, this is false. Yeah. Let us obtain a recursive definition, okay, for the sequence which is an, okay, for an being 5n. Okay, let us look at this now. So a1 for n is equal to 1 will be 5, a2 for n is equal to 2, which is 10, a3 for n is equal to 3, which is 15, a4 for n is equal to 4, which is 20, and so on, right? Now we can write this as a1, which is 5, which is that, and for n greater than or equal to um, 2, we can write as an is equal to an minus 1 plus 5. So this is the recursive definition of the given sequence. Okay. So let us look at another example. Okay, suppose we have an as 6 to the power of n. Yeah. So for n is equal to 1, a1 is 6, a2, n is equal to 2, 6 square, which is 36. Okay. And let us keep this as squares. Okay. To the power, right? 3, 6 cube. Okay. 4, 6 power 4 for n is equal to 4, and we can write this since a is equal to a1 is 6, so a n plus 1 would be 6 times of a n. Okay, this is for n greater than or equal to 1. Okay, okay, so let us look at one more example. A sequence, okay, which is an, is defined recursively. A1 is 4 and an is an minus 1 plus n for n greater than or equal to 2. Okay, let us find an in explicit form. Okay, in explicit form. Okay, so let us look at the solution for this. Okay, so an is an minus 1 plus n, right? Now for n minus 1 would be uh, this will be a n minus 2, right, plus n minus 1, okay, plus n. And for a n minus 2, okay, this would be a n minus 3 plus, yeah, n minus 2, right? This is plus n minus 1, right? Plus n. Okay, further, let us write one more for n minus 4. Okay, so this will be n minus 3, yeah, and n minus 2, n minus 1, and n, and so on. Okay, now if you look at this sequence, so this would be A1, 2, 3, 4, and n. Okay, which is equal to A1 minus 1, okay, plus 1 plus 2 plus 3 and n. Okay, so using A1 as 4, okay, so the standard result of this will be 1 plus 2 plus 3 plus 4 plus n is 1 by 2 times n and n plus 1. So an is 3 plus half of n into n plus 1. So this is the explicit formula for an. Now let us look at another problem to find an explicit definition of the sequence. Okay, yeah, so for a1, which is 7, and an, which is 2 times an minus 1 plus 1 for n greater than or equals to. Yeah, so an is 2an minus 1 plus 1. Yeah, so this is 2 times of 2an minus 2 plus 1 plus 1. So this is 2 times 2 of an minus 3 plus 1. Yeah, plus 1, right? Yeah, close this bracket. So, and this will be 2 cube an minus 3 plus 2 square plus 2 plus 1 and so on. Okay, finally we write this 2 to the power of n minus 1 an minus of n minus 1, yeah, plus 2 to the power of n minus 2 plus 2 to the power of n minus 3. Okay, 2 square, 2 and 1. Okay, further we can write that as to the power n minus 1 a1 plus 1 plus 2 2 square 2n minus 3 n minus 2. Okay, so let us use a1 as 7, which is given. Okay, so this is 1 plus a square and a to the power of n minus 1 a to the power of n and a minus 1. Okay, this is for a greater than 1. Okay, so an will be 7 multiplied 2 to the power of n minus 1 plus 2 to the power of n minus 1 minus 1, which results to as 8 multiplied 2 to the power of n minus 1 minus 1. So this is the expression, explicit definition for the given sequence.